Pulmonary function tests like spirometry are quick and easy to perform and also cheap. Most spirometers are simply a gauge and it measures the volume of air that you exhale. I can't really measure the volume that you inhale, just exhale. I can certainly have you blow up a balloon or a bellows, and I can measure the air that collects in it. In a biology lab, you would probably use a really old-fashioned spirometer that inflates a bellows, which is kind of like the accordion foldy part. And the bellows lays flat when it's not inflated, and then it stretches out when inflated, and you can measure the volume. Um, yeah, kind of like an accordion or a bellows, which is that thing you use to fan a fire. I can directly measure volumes, not all volumes, but enough of them that I can do a few calculations to get the rest. Capacities are things that are calculated. These are volumes that can't be measured directly, but they can be calculated from a few key measurements. If you are sitting down and not exercising, just breathe a few breaths using quiet breathing. Right? Recall that quiet breathing is breathing that only uses the diaphragm and the external intercostals to inhale, right? And you're not using any muscles to exhale. The volume that you are moving in and out is roughly the same with each breath, and that is what is called the tidal volume. So these little oscillations here are my tidal volume. Okay, now you can do the things that I'm asking you to do, but please, if you get lightheaded or dizzy, or if you have asthma or something, don't do it. All right, so now imagine that you're breathing normally, and on your next breath out, you breathe out and continue to breathe out all of the air that you can. You even bend over, collapsing your lungs even more to breathe out. And that volume of air that you just exhaled is called the expiratory reserve volume. And that's this amount, right? It's the amount after your tidal volume that you could exhale. All right, so now breathe normally. And in your next breath in, keep going. Don't stop, right? Get extra air. Keep breathing in until as much as you possibly can. And the extra air that you breathe in is the inspiratory reserve volume. So it seems that you have more volume than what you normally use. Both of these reserve volumes can be used if you need them. For example, if you exercise, immediately exercise asks you to increase the depth and the rate of your breathing. In order to increase the depth of your breathing, you would tap into your ability to move more air with each breath, and you would use these reserve volumes. There's one more volume, but you actually can't measure it on a living person. This is what is called the residual volume. You know what? I think I think I might have seen it called the reserve volume. Residual volume. It's the volume of your lung that does not inflate with each breath. Remember, every time you take a breath, not all of your alveoli inflate upon inhalation. The residual volume it's an estimate of that volume. And it's usually provided on a standardized chart, and you usually have to look it up, right? And the chart is based on measurements from cadavers, right? And the chart's kind of like a BMI chart. You look up how tall you are, how much you weighed, and then you can kind of see the residual volume. So I can measure these three things here. I cannot measure the residual volume. We've now discussed all of the air movement that we could measure or that we could look up. And those were all called volumes because they do come from measurements. You breathe in and out this relatively normal tidal volume, but we found out that if you need to implore more lung tissue, you can tap into those reserve volumes. Okay, so now let's calculate some of these capacities. And to do this, we only need addition and subtraction. So the first thing to calculate is the total lung capacity, which I'll put on our graph here. Total lung capacity. This is the capacity or the total amount of air that could fill your lungs if every single alveolus inflated upon inhalation. To find total lung capacity, we have to add together all of the volumes. We have to add together the IRV, the TV, the ERV, and the RV. All of those together are the total lung capacity. There's also something called the vital capacity, or VC, and we usually refer to it as the forced vital capacity because when you do pulmonary function tests with a spirometer, you are told to forcibly exhale. So the word forced vital capacity is just a reflection of how the testing is done. So forced vital capacity can be calculated by adding together all of the volume that you can use in one big breath. And so forced vital capacity represents everything but the residual volume. And the last capacity that we want to calculate is the functional reserve capacity, or FRC. This is the ERV, or what you can breathe out, and the residual volume, that is volume that is not used, and, oh no, that's it. Just those two. So this calculation, the functional reserve capacity, is what's really important in people with COPD. It's usually very small because they're not breathing out all the way. They're not using all of their reserve capacity as they could. All of the capacities and volumes in the previous slides are really nice, but they're not what's used if you go for your first round of pulmonary function tests. If you are asked to breathe through a spirometer, one volume and one rate will be measured. So take in a really deep breath right now, as deep as you can, and then forcibly blow out all of that air as fast as you can. And now do that blowing out your breath through one nostril. So you might be able to blow out the same volume of air both times, but the rate at which you do it is going to be very different. And this is what we're really interested in when we do pulmonary function tests. Breathing normally, you could probably exhale a pretty big volume of air in the first second of your exhale. But if you're breathing through one nostril, or even worse, like one of those little red cocktail straws that you're not really meant to drink out of, but if you're breathing through a very small tube, you would blow out considerably less air in that very first second. So measuring what you can exhale in the first second can really help us measure restrictive diseases such as bronchitis and asthma. These diseases affect the conducting system, not the lungs. As in our patient, in our case study, he is young, he is healthy, he's an athlete. There's nothing wrong with his lungs, but he has asthma. So if he were to blow out a breath while his asthma is active, he can expel the same volume of air total, but it's going to take him a really long time to do it. And this leads us to the measurement that's most important in asthma. It's called the FEV, or the forced expiratory volume. We can choose to measure FEV at different times of somebody's exhale. One of the ones that's commonly used, and the one that we used in our case study, is we call it FEV1. And what it does is it measures the forced expiratory volume, how much air is exhaled in 1 second. I could measure the FEV2, how much air is exhaled in 2 seconds, and it goes on and on. For a patient with asthma, their FVC might not be any different when the condition is active compared when it's not. The FVC won't change because their lungs are not affected by asthma. but the amount of air that they can expel in that first second will be much different and much less for a patient with asthma. Okay, so if I just measure your FEV1 and my FEV1 and our case studies patients' FEV1s, I'm good, right? I can compare them to each other. No. It's like getting an A in my class and getting an A in my colleague Suzanne Keller's class, who was known as Killer Keller and definitely taught in a much more difficult manner than I taught. So an A in our classes are not really equivalent. If you want to use FEV1, you have to express it as a proportion, as a percentage. So I have an example here to determine why it is that you can't just compare FEV1 across patients. Let's say that we have 3 people here, one weighing 100 pounds, one weighing 200, and one weighing 300. The person weighing 100 pounds loses 10 pounds. That's great. That's 10% of their weight. That's actually a lot. The person weighing 300 pounds loses 10 pounds. That's only 3% of their weight. So the percentage helped me really see how much each of these patients is losing. Both of them have lost 10 pounds, but in terms of the proportion of their body weight, 10% and 3%, that's very different. The FEV1, it has to be put into a percentage form. You have to put it into a ratio form if you want to make a comparison. Even if you have the same patient before and after treatment, you still have to make a percentage of FEV1. The way that you do that is you just divide FEV1 by the FVC. And this is what you will be doing in the lab in order to make comparisons between the standard normal and our patient's success before and after an albuterol treatment. I do not like these two terms that classify pulmonary diseases. I feel like the names, somebody like messed up and they mean to be different. So in reality, restrictive diseases are ones that restrict the rate at which you can inhale or exhale, forcibly or not. Anything that would be like blowing through a straw is a restrictive disease. Bronchitis, asthma. Obstructive diseases are ones that obstruct the ability of the lung to use its total lung capacity. So diseases that eat away at the surface area or fill in the surface area of the lung, those are diseases that affect compliance, and those are obstructive diseases. All right, so now knowing the reality, and like, am I wrong? Doesn't the term obstructive feel more like your 3-year-old swallowed a toy and has an airway obstruction? And then the term restriction feels more like your chest is restricted from reaching full capacity. I just feel like they should be different. So despite my inability to keep the terms straight, they both produce very different curves on this graph. Remember that the key here is that we have to compare the FEV1 as a proportion of the FVC. So comparing these, that doesn't really help us. I mean, we know that they're going to be less, right? Comparing FEV1s, that helps us. I mean, that gives us an idea. But to make a true comparison across individuals, I have to use that FEV1 divided by FVC. Actually, this blue line here is an obstructive disease, and usually FVC is even further out, and this red line here is a restrictive disease. As with our patient in the case study, his FEV1 divided by his FVC is terrible. It's awful. It's in like the 60 percentages compared to his FEV1 divided by FVC with the inhaler, which was close to 80%. Right? So we can calculate this ratio and we can compare it for the spirometry data before and after the albuterol inhaler. So now our patient's trachea and bronchi are wide open from the albuterol stimulating beta receptors of the sympathetic nervous system. And he can achieve FEV1 with much more volume than he did before, right? He can achieve that volume very quickly, and he also gets to his FVC a lot more quickly. So he can blow out more air at a higher rate after the albuterol treatment.